Today we're going to go over graphing rational functions. And you see there are 5 characteristics that need to be part of your graph. You have vertical asymptotes or holes, horizontal asymptotes, you've got your x and your y intercept, and some test points. Now the test points depends on what your graph looks like until that point, how many test points you need to check. You need at least one test point on each side of each vertical asymptote. So here's example 1. F of x equals 2x plus 1 over x minus 3. So the first thing we're going to do is find the vertical asymptotes, and we do that by setting the denominator equal to 0. So we see we have a vertical asymptote at the line x equals 3, and that's shown over here with this blue dotted line. Asymptotes are typically shown with dotted lines. Now a horizontal asymptote we get by comparing the degree of the numerator, the biggest exponent, with the degree of the denominator. And what we notice is the biggest exponent in the numerator is 1, and the biggest exponent in the denominator is also 1. So they have the same degree, and according to our rules for horizontal asymptotes, that means we want the equation y equals the leading coefficient over the leading coefficient. Your book uses the letters a and b, so y equals a over b is our horizontal asymptote. So 2 over 1, which is just y equals 2. And that shows up here as the green dotted line. Next, we'll look for our x and y intercepts. So to find our y-intercept, we replace x with 0. So we want to know what f of 0 is, and that's just negative 1/3. To find our x-intercepts, we're going to replace y with 0 and solve. So we have 0 equal to a fraction. What we're going to do is multiply both sides by the denominator so we can get rid of the fraction. Now it disappears over here. It cancels out on the right-hand side of the equation. And 0 times anything is still 0. So finding an x-intercept amounts to setting the numerator equal to 0. And when we do that, we see we have an x-intercept at negative 1/2. Lastly, we have test points. How many test points? Well, again, we want at least one test point on each side of the vertical asymptotes. So I want to check a test point on the left-hand side, and I want to check a test point on the right-hand side. I probably will need to check more points so that I have a good idea of what this graph looks like. So negative 4, I've checked that one. So when x is negative 4, y is 1. I've checked a test point of positive 1. When x is 1, y is negative 1.5. And when x is 2, y is negative 5. So that's pretty much going along with the idea that this hyperbola, this rational function, looks like this on the left-hand side of the vertical asymptote. Once I get my test points checked, I'll plot those on the graph, and if I can't tell what the graph's going to look like, I need more test points. Here, though, I think we have a pretty good idea of what it looks like, so we go ahead and draw our graph. Another example, x plus 1 over 2x squared plus 5x minus 3. We need to factor the denominator first. In finding our vertical asymptotes, we're going to have to set our denominator equal to 0, so we would want that factored for vertical asymptotes, but we also need to make sure we don't have any matching factors between our numerator and denominator, because those would turn out to be holes instead of vertical asymptotes. Now, after we factor, we can see there aren't any holes because I don't have any matching factors, but we are going to have 2 vertical asymptotes, and when I set those factors equal to 0, the asymptotes are at negative 3 and 1/2, as shown by our dotted line on the graph here. Our horizontal asymptotes we get by comparing the degree of the numerator with the degree of the denominator, and the largest exponent in the numerator is 1, so it's got degree 1. The largest exponent in the denominator is 2, and that's why we have degree 2. So what we have is a situation where we have a smaller degree over a larger degree, which corresponds to a horizontal asymptote of y equals 0, which is just our x-axis. Now let's find our x and y intercepts. To find the x-intercept, we replace y with 0. So I have 0 equal to a fraction, x plus 1 over 2x squared plus 5x minus 3. To get rid of the fraction, I'll multiply both sides by 2x squared plus 5x minus 3, which again like the previous example, really just amounts to setting the numerator equal to 0. So I see that I have an x-intercept at -1. To find my y-intercept, I replace x with 0. So f of 0 turns out to be the number -1/3. And so far then, you can see that we know 2 points on the graph, which is a little strange. Now, once you've done these a little bit, you'll see by experience that typically when you have 3 sections to your graph, the 2 outer sections are going to have that hyperbola-like shape, and they usually will be catty-corner. So if I've got the hyperbola shape in the lower part over here, then probably I'll have the hyperbola shape in this upper corner over here, or maybe it's vice versa. The upper left-hand corner and the lower right-hand corner. Now what happens in the middle is typically a cubic-like shape, so that disco graph, or sometimes it's a parabola, and we won't know until we do some test points what that actually looks like. So test points are the last thing, and I checked quite a few test points here, and I think I'm pretty certain that I know what it does. So plot your test points, and then go ahead and draw your graph. I have one more example to look at. And in this example, we have x squared minus 4 over x minus 2. So I know that this is a rational function, so I'm expecting some type of hyperbola. So I'm going to factor first, x plus 2 over x minus 2, or sorry, x plus 2 times x minus 2 over x minus 2. And we notice there is no vertical asymptote, but there is a hole at x equals 2. The other thing I'm going to look for is the horizontal asymptotes. And what you notice is that there's degree 2 on the top and degree 1 on the bottom. That's large degree over a smaller degree, which means we don't have any horizontal asymptotes. We have oblique asymptotes. And these are graphs that I'm not asking you to draw.